Okay, we are on the kinetic molecular theory and real gas behavior. I'm going to skip the warm-up and let's talk about the kinetic molecular theory. The kinetic molecular theory states that matter is made up of particles that are constantly moving. And when we use the kinetic molecular theory to explain the behavior of gases, we are making a number of assumptions about the size of the molecules, the way that they behave, and what happens and what doesn't happen when particles collide. And these assumptions are included in the postulates of the kinetic molecular theory, which is on the next page. The postulates state, number one, the volume of a gas particle can be assumed to be negligible relative to the space between them. That basically means that it's like non-existent. Number two, gas particles are constantly moving. If they collide with the walls of the container, they produce pressure. Number three, gas particles do not attract or repel each other. Number four, the average kinetic energy of a gas sample is directly related to the temperature of the gas in Kelvin. So let's talk about molecular size. Since the size of gas particles are so small in comparison to the distance between them at room temperature and standard atmospheric pressure, that means that 99.99% of the volume of a gas is actually empty space. So because of all of that empty space, it's easy to compress a gas, so it occupies a smaller volume just by applying some sort of external force. Let's talk about the continuous motion of gas particles. Individual gas particles are perpetually moving in random straight line motions, and they will often collide with each other and then rebound in an elastic manner. So the continuous random motion of gas particles actually prevents them from collecting in one area, and it causes them to be uniformly distributed throughout any container. And we use the term diffusion, where we talk about gas particles moving from a higher concentration to a lower concentration. Let's talk about kinetic energy of gas particles. Kinetic energy is the energy that results from movement, and it depends upon mass and velocity. Mathematically, kinetic energy is 1/2 mass times the velocity squared. The normal distribution of energies in any sample of matter is given here in this figure. And at any given temperature, however, the molecules in all gases have the same average kinetic energy. The average kinetic energy is directly related to the Kelvin temperature, which is this down here. 3/2 times R, the ideal gas constant, times the temperature in Kelvin is giving you the average kinetic energy of gas particles. So as the temperature increases, the average kinetic energy increases. As the temperature decreases, the average kinetic energy of gas particles decreases. Let's talk about hydrogen and oxygen gas. If I have a sample of hydrogen and oxygen gas at the same temperature, both of those gases will have the same average kinetic energy. The average velocity of an oxygen molecule is going to be less than that of a hydrogen molecule because the mass of oxygen is 16 times greater than the mass of a hydrogen molecule. So the heavier particles tend to have slower velocities. And if we take a look at the next section, the elasticity of gas particles, one of the assumptions of the kinetic molecular theory is that no energy is lost during collisions. So that means that collisions are elastic. And the particles do transfer kinetic energy from one to another during collisions, but the average kinetic energy of all of the particles in the sample have to remain constant. Let's take a look at the quick check here. Use the postulates of the kinetic molecular theory to explain each of the following gas laws. Number 1, Boyle's law. So Boyle's law is looking at pressure and volume. If the volume, I'm just going to abbreviate volume with a V, of gas particles is assumed to be negligible relative to the space between them, then a gas is mostly empty space. And if we increase the pressure, it's going to cause the gas particles to move closer together, and that's why the volume decreases. B, let's talk about Charles's law. This is volume and temperature. So if the average kinetic energy is proportional or directly related to the temperature in Kelvin, then an increase in temperature causes gas particles to move faster and further apart, causing a proportional increase in the volume of a gas sample. Let's talk about Gay-Lussac's law, which is pressure and temperature. So if the average kinetic energy of a gas sample is directly related to the temperature of a gas in Kelvin, and the gas particles colliding with the walls of the container produce pressure, then the kinetic energy is proportional to temperature and proportional to the pressure produced by the gas particles. So an increase in temperature is going to increase the kinetic energy that's present in the gas particles, and that's going to result in more frequent collisions with the container, and that's how we get more pressure. Let's talk about Dalton's law of partial pressures. So Dalton's law of partial pressures, this allows us to calculate the total pressure of a mixture of gases. So if the particles constantly move and collide with the walls of the container to produce pressure, and the gas particles neither attract nor repel each other, then the sum of the partial pressures of each gas add up to the total. Let's go to the next page. Let's talk about the root mean square velocity. So the Kelvin temperature is a measure of the average kinetic energy of any sample of gas particles. And through a derivation, we rearrange a couple of equations to get the root mean square velocity, which is the average velocity of a gas particle, okay? And that is stated here. And the root mean square velocity is this mu with an RMS subscript after it. It's the square root of 3 times the ideal gas constant times the temperature in Kelvin divided by the molar mass. The molar mass, this right here, has to be, star this, in kilograms. Okay? And an appropriate unit for velocity is going to be in meters per second, and you'll get this when everything cancels out. So what I'd like to do is, on the next page, let's take a look here at a couple of practice problems. Calculate the root mean square velocity and the average kinetic energy of atoms of argon at 25 degrees Celsius. So the root mean square velocity is equal to the square root of 3 RT divided by the molar mass in kilograms. So this is going to be 3 times, I'm going to use 8.31 joules per mole times Kelvin, and that's back on the previous page. They told you what R value to use for a mole of any gas. And then your temperature, since it's 25 degrees Celsius, if you add 273, you're going to get 298 Kelvin. Divide that by the molar mass of argon, which is 39.95 grams per mole. So that's going to end up being 0.03995 kilograms if you just move the decimal over 3. So this is going to end up being 431 meters per second for the root mean square velocity of argon. Now, if we're solving for the average kinetic energy, it's going to be 3/2 RT. And the R value is still your 8.31 joules per mole times Kelvin. Your temperature is 298. And you're going to end up with 3710 joules per mole. For practice problem number 2, you can scan the QR code with your phone and go over that answer. Let's take a look at the next page. Let's talk about the range of velocities in a gas sample. When the lid is removed from a perfume bottle, it takes some time for that odor to move throughout the air, and that's because of the collisions that are happening between the perfume vapor and the oxygen and the nitrogen particles that are in our air or whatever else is in the air. And the average distance that a particle travels between collisions in a sample of gas is known as the mean free path. And that distance is typically small, and it in the range of about 60 nanometers. And many collisions result in a wide range of velocities as the particles collide and they exchange kinetic energy. And in this figure down here, and the one just underneath it, and there's one on the next page, they're illustrating the velocity distributions for various gases at standard temperature and pressure, and the peak of each curve indicates the most common particle velocity. So here, this pink curve is carbon dioxide. This peak is the most common velocity for a CO2 particle. Carbon dioxide is around 44 grams per mole for its molar mass. And this yellow curve here for oxygen, this peak here is its most common particle velocity. 32 is its molar mass. This blue line for nitrogen, it has a molar mass of 28. And then this green line down here for hydrogen, its molar mass is 2.02. Now, you'll notice that as the mass particle increases, the average velocity decreases. That's why you see carbon dioxide's curve shift to the left, because its speed is lower than that of oxygen or nitrogen, because it has a much higher molar mass. Okay? If we're looking down here at this figure, you'll notice that we have 3 different temperatures. The blue curve is for cold, and the black curve is room temperature, and the red curve is for a hot temperature. And you'll notice that we have a different distribution of velocities depending upon the temperature. So there's an increase in the average velocity with temperature. And there's a decrease in the average velocity at the colder temperature. Now let's talk about effusion and diffusion. So diffusion is where we mix one gas with another, typically from a higher concentration to a lower concentration. And the rate of diffusion is the rate of that mixing. And if we turn to the next page, you'll see here that the distance traveled by gas number 1 over the distance traveled by gas number 2 is equal to the RMS. This is from the previous page where we talked about the root mean square velocity of gas 1 over the root mean square velocity of gas 2. This is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. Now, effusion is when we have a gas that is escaping through a tiny hole in an evacuated chamber. So here you'll notice we have neon and helium in a container, and there's a hole, and the helium, which is a lighter gas, is going to effuse faster than the heavier gas, neon. And if we come down here, you will notice that we've got a figure with helium, and there's an evacuated chamber, and there's a pinhole in between the two. Versus over here, we have ethylene oxide, which is a heavier gas, connected to an evacuated chamber with a little tiny pinhole in it as well. You'll notice there are more helium particles in the evacuated chamber than there are ethylene oxide. That's because the helium is much faster at effusing, because ethylene oxide is a more massive gas. The effusion rate depends directly on the average velocity of the particles. So if I'm comparing two gases, I would use this equation. The rate of effusion for gas 1 over gas 2 equals the molar mass of gas 2 over the molar mass of gas 1. You have to take the square root of that. Let's take a look at some practice problems where we can apply this concept. Calculate the ratio of effusion rates of H2 and UF6. UF6 is a gas used to produce fuel for nuclear reactors. So H2 is going to be my gas number 1. UF6 is going to be my gas number 2. So the rate of effusion for gas 1 over the rate of effusion for gas 2 is equal to the square root of the molar mass of gas 2, which is 352.06, that's for UF6, divided by 2.02, which is the molar mass of H2. This is going to end up being 13.2. Let's look at question number 2. A popular experiment involves the determination of the distances traveled by NH3 and HCl from opposite ends of a glass tube. When the two gases meet, they form a visible white ring of ammonium chloride. Which end of the tube will be closer to the white ring of ammonium chloride? Justify your answer. The molar mass of ammonia is 17. The molar mass of HCl is 36.5. That means inside this glass tube, the ammonia is going to travel faster than the HCl. So that means that this ammonium chloride should be producing closer to the HCl end because it's heavier, and this HCl moves slower than the NH3. Let's go to the next page. Number 2, calculate the ratio of the distance traveled by NH3 to the distance traveled by HCl. So what I'm going to do is I'm going to take the distance traveled by gas number 1 over the distance traveled by gas number 2. And this is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. So NH3 versus HCl, NH3 is going to be my gas 1, HCl is going to be my gas 2. This molar mass is around 17.04, this one is around 36. So this is 36.46 for the HCl over 17.04 for NH3, and this is 1.46. Give 2 factors that must be carefully controlled to ensure the expected result. Well, both gases have to be applied to the ends of the tube at the same time. And the tube can't be disturbed. And then for number 3, you can scan that QR code with your phone, and you can go over those answers. Okay, let's move on to the effects of volume and intermolecular forces on real gases here. So gases behave most ideally when the pressure is low and the temperature is high. You should know that. Real gases do have some volume, and real gases exert some attractive forces on their neighboring particles. And in 1873, Johann van der Waals modified the ideal gas law to fit the behavior of real gases, and he inserted 2 correction factors. The first one accounts for the volume of the gas particles themselves, and the second corrects for the intermolecular forces that exist between gas particles. The van der Waals equation is a more complicated version of the ideal gas law. You will see an A inserted here and a B inserted here, and these are the correction factors. So they call them correction factors A and B. And every gas has its own unique A and B values. So you'll notice on the next page, they gave you those unique values for common gases. And the effect of intermolecular forces and gas volume on real gas behavior is really obvious when you look at a graph of PV over NT versus pressure for real gases, which we're looking at here. Now, here you will notice that we are departing from ideal gas behavior. Ideal gas behavior is this red line going across. And you'll notice that hydrogen is 2.02 for its molar mass, nitrogen is 28.02, carbon monoxide is 16 plus 12, so we're around, or I'm sorry, that's correct. Yeah, 16 plus 12.01, so that's 28.01, and then O2 is 32, okay? So as you are increasing, I'm just verifying my math because I so rarely do math in my head anymore. All right, so you'll notice that with larger gases, we have a greater volume and we have larger intermolecular forces or stronger intermolecular forces. In this case, we are typically looking at London dispersion forces, but as the greater volume and the larger intermolecular forces is becoming more prominent as you go down, because we are increasing the molar mass of our substances and we have larger and larger molecules, the deviations from ideal gas behavior are more pronounced. Okay, now if we take a look at the next page. Here you'll notice that this black dashed line is for an ideal gas. And we have 200 Kelvin for this green line, 500 Kelvin for the red line, and then 1,000 Kelvin for the blue line. And you'll notice that as the temperature increases, the gases behave more ideally because they're getting closer and closer to that ideal gas dashed line. So ideal behavior becomes, or deviation from ideal behavior becomes more pronounced as your temperature is decreasing. Let's take a look at this last page at the quick check. Examine the graphs in figure 8.4.8 and figure 8.4.9. Which particle deviates the most from ideal behavior? Well, it would be O2. Give two reasons. Well, it's the largest gas present, and deviation from ideal behavior is most noticeable for larger gases because they have greater volume. B, what temperature provides the most ideal behavior? Explain. Well, it was 1,000 Kelvin because gases behave most ideally at high temps. And at high temperatures, the volume of actual gas particles becomes almost zero. And also the intermolecular forces become much less noticeable. For number 2, you can scan the QR code and go over that answer. Let's take a look at number 3. Explain the same pattern moving from N2 to CO2 to Cl4, CCl4. And this pertains to the values of A and B. in the van der Waals equation, okay? So for A, this is increasing due to an increase in size, which is because there's an increase in London dispersion forces. And then for B, B is increasing due to an increase in energy levels or layers of electrons, which has to do with there being a larger volume occupied. Number 4, explain the same pattern moving from N2 to CO to HCl to H2O. So the A increases due to an increase in size. So there's an increase in London dispersion forces. And we have dipole-dipole forces in HCl. And we have hydrogen bonds in H2O. Let's talk about B. B is approximately the same for N2 and CO, and that's because we have the same number of electrons, and the volume of their electron clouds is equal because the number of electrons and the size of the electron clouds is greater for HCl and smaller for H2O.